Hello together. Today I want to talk about the matching with a parallel capacitor at the input, and I want to do this in detail today. And this is part of the exercise 1, problem 4. So I have here sketched our matching network. We have here the load impedance, and then we have a transmission line of length L, and at the input we have a capacitor. The load impedance is given by 100 ohm plus J 200 ohm, and we want to consider this circuit at a frequency of 150 megahertz, and we want to match to a source resistance of 50 ohm, and the transmission line has an impedance of 50 ohm. So to use the Smith chart, we first must normalize the load impedance. So the normalized load impedance is the load impedance itself divided by the characteristic impedance, which is a 50 ohm. And as soon as we have the normalized load impedance, we can draw this into our Smith chart. So we have here the normalized load impedance 2 plus J4. And how can I draw this into the Smith chart? I must find a circle of a real part circle of 2. And we must find the imaginary part circle of 4. That this is this circle here. And then we have to draw an arrow between the center of the Smith chart to this point. And this essentially gives us the reflection coefficient, because we have here our Smith chart, which is the impedance plane, and we draw in an impedance so we can directly read out the reflection coefficient. The reflection coefficient can be read out by I take the length of the reflection of this error into the compass, and I use this button scale here to get the absolute value, and we measure the angle. So I have this drawn again here in more detail. Here we have the center of the Smith chart, and we draw to the point 2 plus J4. This is this point, and then this length is given by 0.82, and the angle must always be measured with respect to this axis here, and if you measure the angle, then you end up in round about 23 degrees. So this was the first task of this exercise, to get the reflection coefficient. So in the next task we want to use the Smith chart to match our circuit, and since we have a parallel element at the input, we must switch into the admittance plane. And in the lecture before I showed that you can switch into the impedance plane by mirroring at the point 1. So this red arrow is now the mirrored impedance here. And what we have to do now is we must use the transmission line to transform from the admittance, this is the admittance plane, to the inductive part of the one circle. So here you must remember that we are now in the admittance plane. This means in the upper part we have the capacitors, in the lower part we have the inductances, and here we have the one circle, and we must use the transmission line to transform onto this one circle here. And to read out now the normalized length of the total transmission line, we must draw a line from the center to the border here, and from this center to this border here. And now you see we have two scales outside here, one inner scale and one outer scale. The difference between the scales is that the inner scale has a step here. It steps from 0.5 to 0 again, and the outer scale makes a step here. So to read out the total lengths, now we go into the details here. And so I have here the starting point of our transformation. And we have here, then if I use the inner scale, you see we tick this scale roundabout at 0.469. And here we have a 0.5, so from here to here we have a delta L of 0.031. And now the inner scale starts here again with a 0, and we go all around the Smith chart, and here at the end point of the transformation, and on the inner scale we can read out now a value of 0.297, so that the overall length is given by 0.328. This gives the normalized length. To calculate the physical length, we of course must first now calculate the wavelengths on the transmission line. And since we have an air-filled transmission line, it's just C naught over F naught at 150 megahertz, and this gives 2 meters. Hence we get for the physical length of our transmission line, L is the normalized length times 2 meters, which is a value of 0.656 meter. This will be the physical length of the transmission line. And in the next step, we have to consider the value we have to compensate. So we are here on the one circle, but with a negative imaginary part. We have to compensate the normalized inductive value of -3. So the capacitor, or the normalized capacitor, must realize 3, and this gives the susceptance of the capacitance normalized to the admittance, the characteristic admittance of our transmission line, but this is equal to omega z times ZC. This gives 3. And now we can solve for the capacitance, and if you calculate the value, then we end up in 63.7 picofarad. So to go on in our exercise, we will now switch to the simulation. I have prepared here already my simulation tool. And here we have our network analyzer, and the network analyzer is connected to our load impedance. So of course the 200 ohm reactance of our inductance must be changed to the nanohenry value. And if you now measure or analyze, then we will get this as the scale between 50 megahertz to 250 megahertz, and we can switch on the marker, and then we see that we have here at 150 megahertz we will get 150 megahertz we will get a reflection coefficient of 0.8246, and we had a value of round about 0.83 in the Smith chart, and for the angle we get a value of 22.83, which is very close to the value of 23 degrees which we had found in our Smith chart. And now we must insert our transmission line here. And the length of the transmission line must be 0.656 meter. And as a parallel capacitor in the input, we need a value of 63.7 picofarad. Of course, this must be connected to the ground. And then we can do the analysis again. And then you see that now our marker jumps next to the matching point in the center of the Smith chart. And of course we can have a look, for example, in the log mag format. And then we see we have a very nice matching here. If I include the marker, then I see that we have a matching here of round about minus 30 dB. It's a very good matching. And of course, this finished our exercise now. Thank you for watching the video. Your comments are welcome, and please join again.